this lesson, we're going to talk about Newton's first and second laws so that you can state them and solve problems with them. First, Newton's first law basically says that forces change motion. An object's going to remain at rest or continue to move in a straight line at constant speed unless it's acted on by an external net force. No external net force, no change in velocity. It takes an external net force to change an object's velocity. Keep in mind that velocity is a vector. It has both speed and direction. So if either one of those is changing, there's acceleration. That means there must be an external net force. Let's take a look at an example. We've got an object that has only two forces acting upon it, a force of 30 newtons downwards and 30 newtons upwards. So there's our free body diagram. And the question is, which of the following is possible to be happening? Which is a possible physical situation that could be represented by this free body diagram? So pause the video for a moment, think through that, and then unpause. Assuming that you have paused and worked through that, here there is no external net force. There is no external net force. And we're going to write net force by F net, like that. So these are saying the same thing. No external net force, no F net. So that means that the object is going to stay at rest if it's at rest, or continue moving in a straight line at constant speed. Let's look at the options. It is possible that the object is stationary. That's what the first part of Newton's law says. So that's possible. The object is falling towards Earth. Well, it could be falling towards Earth if there was enough air resistance that it was falling with constant velocity. So it couldn't be in free fall, but it could be falling towards Earth if there was air resistance and it was at terminal velocity. It could be moving upwards in an elevator if it were doing so at constant speed. It couldn't be the very start of the motion when it accelerates from rest, or at the end when it breaks to rest, but it could be sometime in between when it's moving with constant speed. Even though the arrows, the vector arrows for the forces are pointing up and down, it still could be moving sideways. It could be moving sideways at constant speed. For example, this could be the force of gravity and the normal force of a puck on frictionless ice that's moving to the side at constant speed. So this is also possible. It could be moving in any other direction. It could be moving diagonally, so that's possible too. However, it could not be changing direction, because changing direction is a change in velocity, and even though the speed would be constant, moving around a circular track involves change in direction, changing velocity, and so acceleration. And so it's not possible that it's F. An object for which the net external force is 0 is said to be in translational equilibrium. And that means that its velocity will remain constant, either 0 if it's at rest, or whatever else it is, whatever its magnitude and direction is. Translational equilibrium means that the net external force is 0. So that's Newton's first law. Newton's second law takes this a bit further and quantifies how velocity changes when there is a net force. Newton's second law says that the external net force is equal to the mass times the acceleration, or if we want to rearrange that, the acceleration is directly proportional to the net force and inversely proportional to the mass. As the mass gets bigger, the same force will give us a lower acceleration. As the force gets bigger, the same mass will experience a greater acceleration. In other words, it's harder, or it takes more force to accelerate a more massive object compared to a less massive one, and the acceleration is proportional to the external net force, as I said, and inversely proportional to the mass. Newton's second law allows us to solve a lot of problems, and generally the way to do this is to set up a diagram and then figure out from the diagram, from your free body diagram, what all the forces are, and then set up an F net is equal to ma equation. So here, if I've got someone skateboarding down a 6-meter long ramp, remember that we always want to orient one of the axes of our coordinate system along the direction of movement. And the skateboarder is not going to be levitating off or sinking into the ramp, but they are going to be traveling downwards on the ramp. Now, if we set up our, let's actually first put the ramp angle in there. That's 18 degrees, and that's going to be a right angle there. This is also a right angle here. Remember that our free body diagram doesn't indicate the direction of motion, it indicates the forces that are acting on this. So there's our skateboarder, and the first force that we have acting on them is the force of gravity. Force of gravity is equal to mg. in the downwards direction. It's frictionless, so there's no force along this axis, but there is a normal force pointing perpendicular to the surface, like so. That's our normal force. And those are the only two forces acting on the skateboarder. So from this, we can work out the relevant force, the force acting in this direction along the x-axis. And that's going to be the x component of this force. Remember, we saw in a previous lesson that if this is 18, then this angle in here also ends up being 18 degrees. And so the force in this direction, I'm going to draw the component of the weight in this direction along here. The force in that direction there, I'm going to call Fx. This is not a third force, this is just the component of the weight. And Fx is equal to the weight sine 18 degrees. That's how we get the component. And we know g, but we actually don't know the mass in the problem. That's not going to be an issue though, because if we set up our F net is equal to ma equation, we've got this as Newton's second law and this taken from the diagram. We now know that the net force in the horizontal direction is only this red component of the weight. And so mg sine 18 degrees is our net force in the horizontal direction. That's going to be equal to mass times acceleration, and the masses cancel. So it doesn't matter what the mass of our skateboarder is. The acceleration is going to be equal to g sine 18 degrees. Now it's a kinematics problem. The relevant equation with the variables that we need is this one. I'm writing sub x to indicate that we're moving in the x direction. And so that's equal to 2.6 meters per second squared plus 2 times 9.81 sine 18 degrees times the 6 meters of displacement along the x direction. And that gives us the speed at the bottom squared, so we have to square root that to get our answer, and the answer rounded to 2 significant digits is 6.6 meters per second. So there's an example of using free body diagrams and Fnet is equal to ma, Newton's second law, to solve a problem. By the way, just to note that we could also have found the vertical component here of the weight, and because there's no acceleration in the vertical dimension, this vertical component, which would be Fg cos 18 degrees, must be equal in magnitude and opposite in direction to the normal force. So that's an introduction to Newton's first and second laws and solving problems with them.